Hello, my name is Gilles Djomani, and today I'll be presenting on the MUMOX and its applications at the Science Observatory. I would like to take a moment to thank my research advisor, Dr. Phil Muskoff, who is a physics professor at Arizona State University. So a little bit about my personal interest as to why I did research on the MUMOX. I am very fascinated about quantum computers. I think it's revolutionary. I think it's the next big thing. And this research was very much relevant to the hardware development of the foundation, at least, to developing a quantum computer. And so I'm grateful to have learned a lot. I think this is all relevant work to the work that I hope to do in the future. So a little bit about how the MUMOX is being applied at the Science Observatory are examples. Examples of these are in the Science Observatory Small and Large Aperture Telescope. So the small aperture telescopes, the SAT, is what I have here in figure 1, and the large aperture telescope, the LT, is the image here in figure 3. And figure 2 and 4 are cross sections of both those telescopes. And figure 2, if you look very closely at it, you can imagine light from the CMB that these telescopes are designed to observe. If the light was coming down from the CMB, it would go into this window or a lens and then travel down into the detectors where the MUMOX would lie along with other electronics that would work to translate that absorbed information into working data that can be used by researchers at the STEM Observatory to make predictions about the universe. To the left of this very same image, we have an illusion refrigerator, which works to cool down, to reduce the temperature, but also reduce the amount of noise that's being generated from this whole process. And this is also essential to the quantum effect, the quantum aspect of the squids and the MUMOX overall. To the right of this same slide, in figure 4, it's this cross section of the LT. It works very similar to the LT. There's just a few differences, and the main one being is it's much larger than the SAT. So what is a MUMOX, right? I've mentioned it for a few minutes now, and I haven't really defined what the MUMOX is. The MUMOX is the microwave superconducting quantum interference device multiplexer. It consists of an RF wafer, 28 MUX chips, which consist of R squared resonators, flux modulators, DC wafers, which are also called transition edge sensors on bias, and a detector wafer, which is the very first thing that the CMB light will be hitting before traveling down into the processing system of the circuit and other electronics that work to collect data from the CMB. In figure 6, we have sort of a circuit diagram of what's going on inside the MUMOX, where we have resonators in the black color here, and in green we have a flux modulator. In purple we have a RF squared, and in orange we have a transition edge sensor bias, where if the transition edge bias works to send in a current bias through this line, and that current bias creates a change in frequency through their squid. So the squid is this purple section, the R squid specifically. So that creates a change in frequency, which creates a change in phase, which is then collected and travels down on this resonator, and gets transported again into other electronics that processes that as information and data to be analyzed by researchers at the Simon Observatory. So in the next slide, I'm actually going to break down a bit more into details about each of these components that I've mentioned. So there's two types of squids. There's a DC squid and an R squid. The R squid consists of just one junction, and the R squid specifically, it's the same squid that's been used in the MUMOX and the same squid that's been used at Simon Observatory, SAT, and LT telescopes. And the main difference between the DC squid and the R squid is that the DC squid has that has two Josephson junctions, and the DC squid is operated using a DC current, whereas the R squid is operated using a change in frequencies. And the squid overall works to the R squid at least works to when there's a change of when there's a change in frequency, and that creates a change that changing flux at least creates a change in voltage, which allows for the detectors to detect like a qubit and process that as information. There's a lot more details that goes into this, a lot of mathematical details that goes into this. I do recommend checking out some of the citations that I've listed here, and which go a lot more detail into the work that goes into this device. So there are two types of sensors. There's a transition edge sensor and kinetic inductive sensors, just as there are two different types of squids, both being applied in various technologies right now. And specifically to the MUMOX uses the TES in a sensor process. And the TES in this image is specifically in this earlier image that we had is specifically this orange section where you have a current bias going through it, and that would create a change in frequency, creating a change in flux and phase, which is then transmitted through the resonators and into some electronics that processes the whole thing overall. And the primary difference and the reason why the TES is sort of being used in the MUMOX compared to the kids is that it has it's a lot more applicable to in a lot of experiments, and it's much easier to optimize. It just has to vary the frequency and have a low noise, which is essential to the quantum effects required to make sense of this data. But also, one of the few cons that it has is the readout being that it doesn't maybe consist as much of as many readout arrays as the kids, but that can be accommodated for by putting together a collection of detectors to accommodate for the readout. Here we have in this image right here, the black colored section is the RF wafer, which consists of resonators, and resonators specifically the capacitor, the microwave feed line and transmission line and an inductor, which is all grounded. And this circuit, I actually was fortunate to be able to simulate this on AWR, which is a microwave office RF design tool that could be used to make simulations on various different circuits, and it's really essential to the development of technologies like the MUMOX overall. And so if I run the simulation here, I can sort of go over how it works overall. So this is a resonator. So the video is just sort of playing in the background, but I can sort of just speak behind it and sort of explain what's going on. So here I've actually done the simulation prior to this video, and I'm sort of just going really quickly over how to present how to create the simulation for yourself in the software. And right? So now I'm collecting elements and I'm putting them together, and then I do eventually have to tune them, right? So tuning them meaning I want to simulate, right? So I want to see what happens when I vary certain things, and so that's what I'm going to be doing very soon here. So I'm clicking on my capacitor right now, and I'm going to be setting a range between the capacitor values. And right now, actually, I should mention that I've actually already made the changes, but because my screen was recording specifically just um, one window, right? This being the main window, and any tab that I would click on that would pop up would not be part of the video. And so this would have been like sort of where I would search up my elements, and then when I press enter or would click on them, I would be able to add them to the schematic that I have here. And then, right, so now I'm plotting and I'm putting in the, uh, I'm putting the data from schematic 2 that I just created, and I will be getting a plot very soon. So simulate, and there it is. And what is going on here, if I pause the video real quick, is that it's simulating the resonator. So this entire circuit right here is the resonator that's happening, that is in the RF wafer, right? And it's resonating at a frequency of 1 over the square root of L over C, which is the capacitance in the inductor, right? So if I'm increasing the inductor, I'm reducing the frequency at which it's resonating. And if I'm also increasing the capacitor, I'm also reducing their frequency at which this resonator is operating. And so that's sort of what's happening here. Well, I do have, I should cover it. So that's what's going on here. When I'm increasing either values. It's not showing because again, when I pop up a new window, it doesn't let me include it into the video. But that's what's happening here. And so that was a simulation. That was overall, and that was done on AWR cadence. Right. So my future goals are preferably to really continue doing this research. This was a it was a thrill to be able to work on this, and it was a thrill to even to be working on cadence itself, right? AWR, the software that I use, and I'm very thrilled about the work. I hope in the future to, take this entire circuit and put it into the AWR and simulate the whole, mu mux. As crazy as an idea as it sounds, I think it's very much possible. I just do have to break it down, what each individual component is at the circuit level, and being able to um, couple them all together to create a simulation that represents what the mu mux does overall. Thank you.